Suppose we now consider what happens to the compass reading when an aircraft executes a left-hand turn from 045 degrees to 315 degrees through north in the northern hemisphere. To understand what happens, there are two things we have to bear in mind. The first thing to remember is that the example is in the northern hemisphere, and so the red end of the magnet will hang down below the horizontal because of magnetic dip. The pivot point of the magnet assembly will not therefore be over its centre of gravity. Instead, it will be nearer the red end of the magnet. During the turn, the magnet will be dragged to the left by the pivot point, while inertia will react through the centre of gravity. As these forces are not in line with each other, a couple is created which causes an anti-clockwise turning effect, moving the red end of the magnet to the left and the blue end of the magnet to the right, as we look at it here. The second thing we have to bear in mind, and this is fundamental to our understanding of turning errors, is that the compass rose card is orientated to enable the pilot to read the aircraft's heading directly from the compass card. This means that in order for the compass to read in the direction the pilot is facing, the compass card on the instrument will have to be orientated 180 degrees about the cardinal points of the compass. We can see this here, and it will help our understanding if this image is kept in mind. Remember that the compass card is fixed to the magnet, while the lubber line is fixed to the compass casing. So if the magnet swings anti-clockwise when viewed from overhead, the compass reading will increase, or overread. Conversely, if the magnet swings in a clockwise direction, the compass will decrease, or underread. Now let's return to looking at a left-hand turn from 045 degrees to 315 degrees through north in the northern hemisphere. Following the aircraft round the turn, we can see that although the aircraft has turned 90 degrees around the compass, during the same period of time, the magnet has rotated in the same direction by, say, only 70 degrees. Look closely, and we will see that only around 70 degrees have passed behind the lubber line and the compass overreads. In effect, the compass needs to catch up with the aircraft. So when the aircraft is on the desired heading of 315 degrees, the compass is indicating approximately 335 degrees. In order to turn the aircraft onto the desired heading of 315 degrees, therefore, the turn must be stopped when the compass reads 335 degrees or 20 degrees early. The compass will then catch up to read correctly. Think about it. Now let's look at what happens if we carry out a right-hand turn from 315 degrees to 045 degrees through north, again in the northern hemisphere. As before, because of magnetic dip, the red end of the magnet hangs down below the horizontal, and the pivot point will be nearer the red end of the magnet. The pivot point is no longer over the magnet assembly's centre of gravity. During the turn, the magnet will be dragged to the right by the pivot point. However, the inertia will react through the centre of gravity. As these forces are not in line, there will be a couple causing a turning effect, moving the red end of the magnet to the right. Although the aircraft has turned 90 degrees around the compass, the magnet has been rotated in the same direction by a small amount, say 20 degrees. We have only seen 70 degrees pass behind the lubber line, and the compass underreads. In order to stop on the correct heading of 045 degrees, the turn must be stopped on 025 degrees or 20 degrees early. Let's suppose we turn an aircraft to the right from 135 degrees to 225 degrees through south in the northern hemisphere. Once again, because of magnetic dip, the red end of the magnet hangs down from the horizontal, and as before, the pivot point will be nearer the red end of the magnet. The pivot point is no longer over the magnet assembly's centre of gravity. During the turn, the magnet will be dragged to the right by the pivot point. However, the inertia will react through the centre of gravity. As these forces are not in line, the couple created causes a turning effect, moving the red end of the magnet to the right. If the result of this is difficult to envisage, remember that we are now facing in a southerly direction in the northern hemisphere. Although the aircraft has turned 90 degrees around the compass, this time the magnet has been rotated in the opposite direction by a small amount, say 20 degrees. We see 110 degrees of heading change briefly, and the compass overreads. In order to stop on the correct heading, the turn must be stopped when the compass reads 245 degrees or 20 degrees late. By now, we should be able to work out on our own what happens when we turn from 225 degrees to 135 degrees in the northern hemisphere through south. Click on Continue when you have decided what compass heading you must stop the turn on. The answer is that we are turning left, and we should stop the turn when the compass reads approximately 115 degrees, or in other words, 20 degrees late. As before, because of magnetic dip, the red end of the magnet hangs down from the horizontal, and the pivot point will therefore be nearer to the red end of the magnet. The pivot point is no longer over the magnet assembly's centre of gravity. During the turn, the magnet will be dragged to the left by the pivot point. However, the inertia will react through the centre of gravity. As these forces are not in line, the couple created will cause the red end of the magnet to move to the left. As with the turn to the right, from 135 degrees to 225 degrees, we should stop the turn late. As a general guide to how soon or how late to stop a turn, it is worth noting that for a rate 1 turn, the turning error will be approximately 20 degrees. Rate 1 turns are commonly used in instrument flight, and in a rate 1 turn, it takes 2 minutes to turn through 360 degrees. For a rate half turn, allow a turning error of 10 degrees. And for a rate 2 turn, allow a turning error of 30 degrees. To conclude the lesson, this table summarises turning errors in the northern hemisphere. In the southern hemisphere, the errors are the exact opposite. The term sluggish, which appears in the right-hand column, means that the compass heading is lagging behind the aircraft heading. Liquid swirl will increase the turning error. Conversely, when the term lively is used, the compass heading is leading the aircraft around the turn. Liquid swirl in this case will reduce the turning error. The following rules apply. During a turn through the pole which is physically nearer the aircraft, the compass will be sluggish. It is therefore necessary to stop the turn early on the indications given by the direct reading compass. During a turn through a pole which is physically further from the aircraft, the compass will be lively. It is therefore necessary to stop the turn late on the indications given by the direct reading compass. At the magnetic equator, there is no dip. Therefore, the only turning error will be due to liquid swirl. Liquid swirl may account for a compass heading lag of around 5 degrees, or 5 degrees sluggish. Remember, it is the displacement of the magnets in a clockwise direction when viewed from above, which causes the compass to underread. A displacement in an anti-clockwise direction causes the compass to overread.